Okay, everyone. Thank you for being here to this lunch colloquium. Today we have Niccolò Ciolli that is a PhD student visiting from DTU and is visiting Kim until the end of March. And before I give the floor to Niccolò, I wanted to stress that there are still a couple of openings for April, and in particular for the 15th and the 29th for lunch colloquia. So if you know somebody or you want to present, please don't hesitate to contact me. And also from next week, there will be the start of the online lunch colloquia in which people from around the world will be invited to give some presentation online. On the 11th, there will be a professor from New Mexico, and then we have people from Stanford and others. And also in that case, if you have peers that would like to have a talk, but they are on the other side of the globe, but they would still be, they would be more than welcome to join to this online version of the lunch colloquia. So without further ado, I leave the floor to Niccolò, that is going to talk about tensor for machine learning today.
Thank you. So, I'm Niccolò, nice to meet you, and I'm a PhD student from DTU. And my PhD project is about generally tensor networks for machine learning, and will specifically focus on density estimation and polynomial regression in these talks. So, I will firstly introduce why one would be interested in tensor networks, what they're useful for, and what are the main advantages. Then we will speak a bit about what are tensor networks, what is the tensor networks notation, and then I will propose some window in what has been my work in the first year of the PhD, which is using tensor networks to do density estimation, and then using tensor networks for polynomial regression. So, tensor networks, firstly, are a way to represent highly dimensional data in a compressed way using contraction and interaction of smaller dimensional objects. Indeed, tensors, more generally, are simply a zero-dimensional tensor is a constant, a one-dimensional tensor is a vector, two-dimensional matrix, and so on, right? So it tells you, basically, it represents objects in higher dimensional spaces. Indeed, the coefficients of an element in a high-dimensional space usually scales exponentially with the number of dimensions. Tensor networks are a way to represent these high-dimensional spaces in a way that the number of coefficients that represent the object scales linearly with the dimension. So they were introduced in quantum condensed matter in the 1950s and farther on. And they were indeed developed because usually in quantum condensed matter, you often have a system of hundreds and thousands of particles, often needing to represent tensors and coefficients that scales as 2 to the 1000. So computationally, this is infeasible. And so they came up with the idea of representing the tensor through the interaction of the particles with small objects. So they can be used wherever you can have a high-dimensional parameter space and where you need interaction between these dimensions. So for example, indeed, what I will present today, density estimation, often the joint probability distribution, it will scale exponentially with the number of variables, right? For example, the joint probability distribution of binary variables, if you have 10 binary variables, it will be an object of 2 to the 10 number of parameters. So usually representing a joint probability distribution scales very badly. Let's just say if you want to represent the full space of the probability. And then the other application, which is polynomial regression specifically, but more in general, function approximation. When you have a function basis, like it could be polynomial or Fourier basis, and you want to represent a function as a series of a basis and a set of parameters, the number of coefficients for multivariate functions scales, again, exponentially or combinatorically. So both cases are cases where you have the representation of your problem that scales in a way that is not feasible for the hardware usually. So, what are tensor networks? And I will try to introduce on this tensor network notation, where basically it's a way to graphically represent tensors. Okay. So, very trivial example, we start on the left with a vector. This is a representation of a vector where we have each node. I mean, these tensor networks can be represented as graphs, right? Where the nodes represent tensor and the edges of the nodes are the dimension of the tensor they represent. So, for example, on the left, we have simply a vector, the element E of a vector. So, vector, one-dimensional tensor, one free edge. Okay. So, in the middle of A, this A is a matrix. The element ij of a matrix, you can still count the free edges to know which tensor they are representing, the tensor networks, in this case a two-dimensional tensor. And then when the edges are connected to nodes or to tensors, what they are doing is a tensor contraction, which is simply a multiplication over the shared dimension and the sum, right? So in the third diagram on the right, we can see how to represent as a tensor network some matrix multiplication. So now, an example of a tensor network, a very popular one, let's say the standard one, which are called the tensor train, is given by this object. And you can say it represents an element of a three-dimensional space, and it does so using a contraction of three tensors, right? So you can say that it is represented by two matrices, A1 and A3, and then another three-dimensional tensor, A2, that contracts between them. But basically, the full contraction, after we exhaust the sum, it will give you an element of a 3D space. Just to make it clear. Okay, now let's see how it can be used for density estimation. So, an example to represent a joint probability distribution would be to use mixture models. Mixture models are basically saying, have an assumptions that you start with independent probability of your variable, and then you can do a linear combination to get the full joint probability with different coefficients. So, in this model, what we have, x, y, z, are some vectors, are the input nodes, and their dimension depends on the parameter, for example, alpha for x. So what does it mean? That the node x basically contains a set of value for probability distribution of x for different alpha parameters, right? So you can create this space. And then you say that you assume that the joint probability distribution has the form that is given by the equation on the right, right? It's just simply a sum over a big multidimensional tensor of coefficients that mix all these different configurations of the probabilities. Now we can indeed decompose this A coefficient as a tensor network with the same structure that I showed you before, which is the tensor train. So now first I explain a bit. In this decomposition for probability distribution and density estimation, we assume, we do two main assumptions. Firstly, the nodes of the decomposition are value greater than 0. And second, that they are properly normalized with respect to certain dimension. With this assumption, you can show that this decomposition is actually representing a graphical model for probability distribution. What I mean that each node now has also probabilistic meaning, contains information about the probability distribution. Specifically, in this case, it is an hidden Markov model, right? Where you have indeed hidden states that go over the ranks or with the R dimension of your decomposition, and basically they define in this way, and with the proper normalization, a graphical model for a probability distribution. So what it is done, at least in my project, is basically to assume that the coefficient of a certain probability distribution are already decomposed as a tensor network, and we want to learn the value of the nodes and also the parameters of the x, y, and z distribution. You can easily do so using expectation maximization, because it also naturally gives you the right normalization, right, when you do the expectation maximization algorithm. But so, now let's speak what are the main advantages of representing a probability distribution in this way. Basically, the main important properties is that in this factorized, let's say, model for a probability distribution, integrals respect to variables, they get factorized as well, right? So, for example, if we integrate over the x variable, you have to perform not the integral over the full joint distribution, but it can be only the integral of the node representing the variable x. This is very useful, especially because, first of all, indeed, dealing with probability distribution is also always, very expensive if they occupy a very big space, let's just say. And in this way, operation like marginals, expectation becomes basically free. Because, for example, marginalizing over the variable x, it is just integrating the node containing the value of probability of x given alpha e that we had in the previous slide, one on the bottom left. Integrating over the variable x, marginalizing, it just means substituting the node with a vector of ones. And so you simply contract the whole tensor, and what you get as an output is the marginal probability distribution with respect to x, which is very inexpensive in this way. Same for expectation, but instead of substituting one, you substitute the expectation value with respect to the probability distribution of the node. So just still, it's a matter of computing a vector and do the contraction of your tensor network. Also, you can sample with the assumptions that we had. We have that all the nodes represent a probability distribution. And so you can simply start with a random state, and then with the full knowledge of how the probability distribution, or say the information transfer through your model, you can sample node by node, let's just say, and have, generate data. And then it can handle heterogeneous data. Indeed, there is no need of, there is no constraint on the probability distribution that you can have as nodes, and they can also handle different distribution for the same density estimation. For example, you can have a model that you have one feature that is continuous and one feature that is binary. Just put everything in the model with the proper probability distribution and can handle that and find all the coefficients. So in our work, we thought what basically one can do to exploit all of these probabilities, these properties. And basically we came out with trying to learn partially observed data and to do imputation. Learn partially observed data because during the learning you get presented with some data set where, for example, in a sample, there is a missing feature, right? So what you do, simply you substitute the missing feature with a 1 instead of the none, and you're simply learning a bit the marginal part of the distribution for that specific sample. And you can do like this for all type of variables, no matter their underlying distribution. And then imputation, because impute would be to generate the data with the knowledge of the full distribution. And so what you can do with these models is, I think, in my opinion, even better than just generating data, because you can compute the expectation of the missing variables conditioned to all the other variables in that sample. So it would be like the mean of infinite samples, right? So now I just show some small results for say, very small data set and with very small models. But basically here we report the error rate of the imputation in function of the percentage or the fraction of missing data of the dataset, right? We artificially generate the missing data with more seeds, and the model that are Tensor Networks model are the one with the dot, the CP and the TT. And then we compare against some standard models, which could be KNN, MIN, and some deep learning model, right? That are MIDAS, which is a deep neural network, HIVI is a variational autoencoder, and GAIN is a generative model. So we compare a bit the results on imputation. So higher is worse because it's the error rate. Right? So they perform, would say, well in most of the data, then some pretty bad, especially in the tic-tac one. But yes, this is it. So it seems that they work. Now I will speak about regression. So the jump here is that with the same structure that we've seen that does a probability distribution, lifting the constraint that the nodes must be greater than 0. So now our nodes can live in all R. And the input now are no more probabilities, right? But are just features or maps from feature spaces. We can use the same structure to do regression. Of course, it changes the learning algorithm. But okay. So the problem of regression is simple. We have model prediction, but what is it? The prediction of the model will be this Y. And then we consider A as the learnable parameter of the model, which is a tensor, because phi S is basically an high-dimensional map that takes your features and embed them in a higher dimensional space, in a tensor. And so what here is done is simply a tensor contraction. Okay, so then you get a constant. The loss that we study is the simple mean squared error in this presentation, and then we use for learning the Gauss-Newton update. So the question here is basically the update, the optimal update for one node of the tensor network A called AI, right? So the node I will be, you can get the update for the node I, computing the Hessian respect to the node I, which will be the second derivative of the loss respect to the node I. And then you can equate it to the Jacobian respect of the node I, which is the first derivative of the loss respect to the node AI. Okay? So now that we spoke about derivative, let's show what they mean for a tensor network to derive respect to a node. And simply, we can see it, we can call it, like to call it as the environment of the node. So simply, on the left, given a tensor network A and identified a node A, you can compute the derivative with respect to the node IA as the contraction of the full network, excluding the node you are deriving respect to. So basically, the output of this tensor network is itself. It represents a tensor with the same dimension of the node you are deriving respect to, right? As expected. Now, with this notion, we want to just simply show graphically how the update equation would look like in this tensor network notation, right? Also to emphasize why this Gauss-Newton method and second-order method usually with tensor network become pretty, I wouldn't say trivial or simple, but the equation is not that hard to derive, I guess. Okay, but first I will speak about the polynomial map that we use in this work. And basically what it does is defined as given x, which would be for a sample, the vector of your features. First, we map x over x tilde, where x tilde is simply appends a bias over to your features, right? So just add a 1. And then you consider the full map in the space as an outer product, a repeated outer product of the same x tilde. This, you can see it's a polynomial map because the number of times you do the outer product of x tilde with itself is the degree of the polynomial, right? That you are creating, of the polynomial coefficients that you are spanning. Right? The outer product is just multiplication with itself in all possible combinations. And the bias one is basically there because you not only have a certain degree, but also have all possible combination of lower degrees. So this map phi effectively takes feature vector and output you the full space of all possible coefficients that can appear in a polynomial, right? And in this case, this map is also degenerate because it gives you all the possible combination without counting identical combination. For example, x1, x2, and x2, x1 will both be in this map. Okay, so it's a degenerate. Okay, with these assumptions or these constructions, we can write the structure of the prediction of the problem like this. Simply, A, again, are the black coefficients represented as tensor networks, and the full tensor of the feature map, assumed it can be written, constructed as a product, as an outer product of vectors, can be simply represented like this, which is the same structure that we already saw before, right? Where you have input nodes, in this case are repeated features with added a bias, and then a set of coefficients that give you the tensor of the mixing, right? Okay. Then we have we can compute the Jacobian given this tensor. In the Jacobian, the derivative of the loss with respect to the node, to a certain node I, it will be simply the environment of the node AI, which has this structure, contracted with the input, for example, S. So the full Jacobian equation can be simply written as a weighted sum over the derivative of the loss. L represents the loss for a sample. So it's the first derivative of the loss with respect to its own argument, multiplied that weights the environment of the node that we are deriving respect to. Also, the Hessian has a simple form, I would say, but it's simply the weighted sum respect to the second derivative of the loss of what? Of the outer product of the structure of the environment that we saw before, right? So basically recycling computation, and it makes things easier, at least, to compute it correctly. Then we can write the full update equation, still with the structure, where we have simply the Hessian that contracts within red the optimal update for the node, and then we equate this to the Jacobian. Okay? So structurally, that's how it looks like, the update equation. And then to get delta AI, you simply have to solve a linear system. Okay, now I just show a super toy example of a one-dimensional polynomial and how it's reconstructed with this model. So basically, given noisy data, one thing that I didn't mention about the learning is that what you do usually is that you start with a node, then you calculate the best update, you update it, and then you leave it like it is, and then you go to the next node, and you keep swiping through your network one node at a time, right? So it's effectively solving a sub-problem as a second order. Okay, this is just to show a bit of a reconstruction, very fast coded in Go, to just see that it works. So the application that we do in our work are a bit more general than the example that I show. What we do is we consider different losses, also to include classification. So we consider mean squared error and cross entropy. Indeed, as you could have noticed from the update equation, the form of the loss is never exploited. You just need to find the first derivative and the second derivative with respect to the output of the model, in this case, which are the argument of the loss. And you can extend it to classification or to any losses in reality. Then we will have multivariate inputs, indeed, not just one-dimensional functions approximation, but generic multivariate inputs. And then we add also, need to do classification. We just add a free edge, which would be the output dimension, right? So when you contract everything, what you're left is just a certain output. And then we study how regularization affects this model and how it is introduced for the second order updates. Okay, this is a type of structure that we study, which is basically, you can recognize what we showed before with a simple tensor train, where black still have the same coefficients with an output dimension, blue are the input nodes, and now introduce this red tensor network, which is called the matrix product operator, which effectively what it does is a compressed representation of a linear transformation from the full span of the coefficients of the polynomial to the space of the coefficients. Okay? So we do this because this gives you the power to do, let's say, indeed, the transformation of the inputs in their mapped space, let's say, their embedded space. The type of usage is this red network, this matrix product operator, can be fully learnable, and this is just then simply a linear transformation that can be a compression of the space, but then can be structured, which means acting only on a subspace of the input that would have the same meaning as a convolution, for example, for images and these things, or it can be completely not learnable, for example, and act as a mask. Indeed, as I said when speaking about the polynomial map, the polynomial map is degenerate, and you may want to impose symmetry through a mask. The nice thing is that this mask doesn't have to act on the full blown up space, but can act on the subspace and interact to pass the information of which coefficients is masked, right? So basically, in the mask case, these red nodes will be hyperdiagonal and upper triangular elements. But effectively, what they do is they trim out all the degenerate coefficients of the polynomial. So, conclusion, what can benefit from tensor network? And I would say whenever your problem has a parameter space where you have multiple dimension that keeps increasing once you add complexity, and so the dimension of your parameter space explode, let's just say you could use tensor network and it could benefit you. It's not a given. Then tensor network, I believe that naturally, let's say, accommodate for second order learning. Indeed, most of the learning algorithms for tensor network are second order in the update, which means faster convergence. And the sub-problem, now in this regression case with mean squared error, the sub-problem are convex too. And then at the end, some application that come out in the latest year is a bit of this classical quantum hybrid algorithm, where basically you can train a model or compress it as a tensor network. And since tensor network can be say, prepared as quantum state, what this hybrid algorithm trying to do is to learn the model classically and then trying to embed it in a quantum hardware to make him do some work, depending on what's needed. Okay. And this was it. And if you have any questions, thank you.
Any question?
Yes.
No, so I think in the first part you talked about how it looks like a probabilistic graphical model, and from my understanding, probabilistic graphical models are also used to save space in some senses, right? So that you don't have to store the entire joint probability distribution. You can save the factorization. But what I guess I got lost was that how the tensor network comes in contact with the.
So there are different ways, I believe. I don't know if you're familiar with something called probabilistic circuit or some product networks.
Yeah.
Basically, there is actually a paper which came out while I was writing indeed this one that says that tensor network like these are exactly probabilistic circuit and some product networks. Just you see the parameter in a different structure, but we can very well extend it. The graphical part of it, see where it is. I would say come from the fact of when during the update, right, you decide to use the expectation maximization algorithm and normalize over certain dimensions. Indeed, if you see the dimensions that are associated to certain modes, they give you effectively a direction, right, of your probability distribution, where is it going. So for example, you have the lambda that is associated to R2 and to beta j, which effectively takes information from the R1 hidden space, that R1 in the space, and propagates it forward, right? So I would say the way to make this circuit, so my graph, probabilistic graph, is basically giving it a direction, make sure that it's not cyclic, right? And that ensures you that it's a probability distribution. And this is done by, indeed, ensuring a normalization and with the meaning, right, of your construction. So if you have a direction, indeed, you can't just randomly construct a tensor network and impose whatever normalization of the modes. It needs to follow these properties to be exactly, say, a graphical model for probabilities. Yes, please.
Yeah, thanks. So I'm just wondering, why do you compute the update on a node-by-node basis instead of across the whole network in one pass?
Well, because mainly, usually, if you think of very high-dimensional spaces, usually you can compute the space that the Hessian occupies, right? And it's usually way too huge, right? If you want to do the full spaces. Also, I would say tensor network has this nice property that are linear in the nodes. They're linear mapped in the nodes. And so it's very, let's say, straightforward to compute the Hessian respect to a single node, because actually there are algorithms that takes 2 nodes at a time, right? But since the main, let's just say, concern is the space reduction, doing the full Hessian would simply give you the best update of the full not compressed tensor, right? So it would be again a step 1. And so what you want to do is to learn subspace by subspace to keep this decomposition alive, I would say. But indeed, there are algorithms that also consider 2 nodes together, update them, and then split them again. But already with 3 would become a bit heavy on the computation.
Yes, I have a quick question. It might be a little bit silly, just elaborate. So what I understand is that at the end of the day, you have a model which is linear in parameters and some bases. Right?
Linear in parameters?
Yeah, linear in coefficients.
Yes.
And for example, in the case of regression. And you have some bases which are characterized based on this monomials or. So I'm wondering about the magic of the tensor networks, because pick any radial basis function or any type of basis, more or less I have same structure.
Yeah.
So I'm wondering where is or if I use like something like a coordinate descent for the optimization, it's like more or less like node by node optimization. So I'm wondering where is the magic, where is the because you have a structure and you're exploiting the structure.
Yeah.
I'm asking for that. So I'm new to the topic.
You're asking how are we exploiting the structure?
Yeah.
But I would say that indeed the main thing of tensor network is that you're representing a full tensor, but never really computing it fully below, right? So what is in your memory is simply the collection of the nodes. Indeed, if you see, also for example in this image, what you never do is to contract fully the nodes on the top and then fully the one on the bottom, right? Because at a certain point in the computation, you would have a 3-dimensional tensor. I mean, in this case, it's 3-dimensional because it's small, also the middle ones. But what you do usually, right, if you contract this and this and this and the upper one, you never really have to have in memory something that is the fully blown dimension, right? So you can really operate subspace by subspace without never have to have these concerns. So that's, I think it's the main advantage.
Thanks.
Thank you.
I have a question about applications, so it's a bit far maybe from the talk of today. I was wondering, when you have a problem, when you have a PDE in high dimensions and you want to solve it numerically, you do something like finding differences, you have this grid, the number of nodes that is exploding. Can you use tensor networks to make that problem?
So if you have a grid with nodes, I would say yes, because it's usually where they're used, right? In lattices of spin problems. So for sure, that's where actually they naturally are embedded. Now, the thing is that if you usually study density on these grids, there are different ways. This is one way that I presented. There are also other ways where your tensor is now not just the coefficients of the mixture model, but the output legs of your tensor give you the value of the probability in that point, right? And in that, you have to consider different structure to ensure that the probability is normalized and positive, which are, well, usually are called these locally purified states, but they're very used indeed in quantum, and indeed also there for a lattice or a grid, you need the probability, right? The distribution of your spin model. And for sure, I would say that would work well. If it answers your question. Thank you.
Okay, if there is no any other question, we can thank the speaker one more.